So previously we learned what a tree was. However, it's a pretty restrictive idea. Most graphs are going to have a cycle somewhere, and so they're not going to be a tree. However, even if it's not a tree, it turns out we can find something called a spanning tree. And this is going to be a very useful concept. We'll see an application for this in the next video. But the idea of a spanning tree is that we would like to take part of the graph, enough that we can reach every vertex, but not too much that we are going to no longer be a tree. So for example, if I were to make a simple graph with 4 vertices here, this is definitely not a tree because it has a circuit in it. However, if I were to take just these 3 edges and draw this graph right here, this is a subgraph of the original graph, and this subgraph is a tree, and it contains every vertex, so therefore it is a spanning tree. I do want to point out that there are generally lots and lots of possible spanning trees. For example, if I were to take those 3 edges, I would get a different spanning tree. So keep in mind that there is not just going to be one spanning tree on a given graph. Generally, there's going to be a lot of them. And we have this nice useful theorem here that says that as long as you have a simple graph, it's connected if and only if it has a spanning tree. So basically, as long as I give you a graph that's connected and I ask you to find a spanning tree, you are going to be able to find at least one of them. It's guaranteed. Now, we could, when we're given a complicated graph, just try randomly picking things and hope that we end up with a spanning tree, but that's not a really great plan there. We could also start with a big graph and start trying to remove edges at random, hoping that we're going to get a spanning tree. But turns out that there are other ways that are more efficient that will get your tree guaranteed here. And 2 of those ways are going to be called depth first search and breadth first search. Now, there are going to be some random choices in these algorithms, which means that you are not guaranteed to get the same answer as someone else doing it. We are going to see other algorithms dealing with trying to find spanning trees in some sort of optimal way, but for right now, these at least will work here. So for a depth first search, the way we're going to do that is we're going to say, okay, pick any vertex to start at random. And you could pick whatever one you want. Now, a lot of times when I give a problem like this as an assignment, I will force you to pick one. And so I'm going to go ahead and pick this upper left vertex here to be my starting vertex. And what I'm going to do is I'm going to randomly pick any edge I want to, starting at that vertex, and I'm going to put it together. So I'm going to go ahead and go down in this case. There would have been nothing wrong with going right here, but I just randomly chose to go down. Now the way that depth first works is I'm only going to add one edge at a time, and in some sense I'm going to keep trying to dig deeper and deeper into my graph here in some way and use that to get information. So I'm going to then choose to go down again. I choose one random edge that's connected to that, and I continue going. Now at this point, there's only one way I can go, which is right, so I can choose to do that. Now at this point, I could go down or I could go up, and from us as looking at this problem from overview, right, look, we see the whole thing all at once, it might make more sense to go down first and work your way around. However, a lot of real-world applications, you don't really get to see the big picture all at once. Especially if you're writing a computer program to do this, they might not be able to visualize the whole thing and know what's best. So let's suppose I chose to go up here. If I really am randomly choosing, left, right, up, or down, I might choose to go that way. Now, at this new vertex, there are 3 directions I can go, left, up, or right. However, if I were to choose to go left, that would not be a valid choice because I would be forcing a circuit there and I would no longer have a tree. So that does restrict my choices. So instead of going left, right, or left, up, or right, I'm going to go up or right, and I'm going to choose to go up. Now, when you're doing this, it might make sense to keep track of, what order you've put these in here, so anyone else could follow along later. This is also something I'm going to require of you on your homework and exams, so that I can keep track of what you did, make sure you're doing the algorithm correctly. And again, let's suppose I choose to go right here. That would be 6. And then I will choose to go up here, 7. And then I will choose to go left here, 8. And at this point, once I've done 8, there's only one direction to go down, and I can't go there because I'd be forcing a circuit, no longer a tree. And so when depth first search, when it gets to a point where it can't go any further, you go back one single vertex to right here, and you ask, is there any other direction you could possibly go? And there is. So I would go right there, and I would get my 9. Then I would say, is there anywhere I can go from that point? And I can go down 10. And I can't go left. I could go down or I could go right. I'm going to choose today to go to right here, 11. Then I have to go down 12. Let's say I go down again, 13. Only one choice here to go left, 14. And at this point, I can go down, left, or up. I'm going to choose to go down, 15. Then left, 16. Left again, 17. And then notice that I cannot go up there. So I have to go back to the previous node and see if there's another direction. There is. So that's 18. Then I can't go left, I can't go right, so I'll go up. That's 19. I can't go left, I can't go up, so I will go right. That is 20. And then we want to check here, is there any vertex which I did not reach using the edges that I have drawn in blue here? And it looks to me like I do in fact reach every possible vertex. So therefore we get the spanning tree here, and we can double check how many total vertices we had. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So there was 21 vertices, which meant that we knew ahead of time that there should be 20 edges from the theorem on the number of edges in a tree. So that would be one example of a depth first search on this graph. Now again, the key that makes this a depth first search is you are always just adding a single edge at a time and essentially going as far as you can before you have to stop. And then when you stop, you backtrack one place and see if there's anywhere else you can go from there, and then continue on. Okay, now for a breadth first search, we are going to do this a little bit differently. So if I start at the same node here, just to give it a better comparison, instead of adding one edge to it, I'm going to add every edge I possibly can to this. So all in one go, I'm going to add both 1 and 2. And you get to choose whatever order you want to number them in, doesn't really matter. But once you've added every possible edge, then you go to the lowest number edge, which is 1. I travel along there, and I will add every possible edge I can to that. So I will add this, this, and this. So that will become 3, 4, and 5. And then you're going to go to the smallest number edge, which is back now 2 now. Go to the end of that and add every edge you can. Now I can't go right here. It would form a circuit, so I'll go down. That's going to be 6. Then I look at the smallest number edge I haven't done, which is 3. And I add every edge I can, so that's just that one there, 7. Then I look at the smallest number edge, 4 here. And 4, there's 3 directions, but one of them going up would not work. It would close off a loop, so that'll be 8 and 9 there. Then I would go to 5. and say, okay, 5, where can you go? You can go left, right, or down. I can't go left or right, so I'll go down here. That's going to be 10. And then I'm going to keep going on here. I go to 6. I can't add anything that's 6. 7, I can. That's 11 there. 8, I can add 2 of them here, so 12, 13. 9, I can't go left or right. I can go down, 14. 10, can't go left, can't go right, can go down, 15. 11, can't add anything to that. 12, I can go down there. That's going to be 16. 13, can't go left, can't go right, can go down. That's 17. 14, no left, right, down. That's 18. 15, can't add anything to that. 16, I can go down. 19. 17, I can go down. 20. And at this point, nothing else can be added without making it no longer a tree. And that's how we work here. So again, breadth first is you're adding a bunch of edges all at once. Depth first is you're only adding one at a time and going as deep as you can, and only backtracking if necessary. So there are different algorithms. They are going to give you different answers, but they both work to find a spanning tree.